Hi, this is another circuit, another example circuit where you can apply this method 3 on, handwritten Boole's algebra simplification. So from a circuit like that, okay, you can very well obtain the truth table by hand, going through the several expressions that can be derived from the initial circuit and the initial algebraic equation. So this is the picture of the circuit, okay, and here you have a network of gates, of several type of gates connected together in some way or another. So the objective is just another drilling exercise for getting in touch with the analysis process, right? So this is the symbol, and it looks like the same, D1, D0, A and B, and the objective is to find the truth table, which is key. So key is going to be a function of D1, D0, A and B, pretty much as the circuit C, right? Just another time. So the mechanics of the method number 3, which is applying the Boole algebra in a paper and using a pen, it is like that, You have now here a circuit, all right? So the circuit is going to be written as an equation. So you will have at the very beginning, the equation which is the exact translation of this circuit. That's the idea here, all right? And from this initial equation, from which, if you like, you can come back to the circuit or vice versa, it is the same idea. From this initial Boole's equation, you can continue down to the truth table, trying to simplify using algebra, right? In one way or another, in the end, or just not in the end, in the middle, you will have a concept like the product of sums or the sum of products, doesn't matter which, right? And this is, a very simple expression which is perfectly equivalent to the initial one, but a lot simpler. You have simply a product of some sums or a sum, or of some products. That's the idea. So, in order to reach the final truth table, there is only one thing to do here, and this thing is to try to add the missing variables in every one of the products or in every one of the sums, so that in the end you get what is called the product of maxterms or a sum of minterms, which is already the truth table in an equation, in a canonical equation form. So that is going to be the mechanics, okay? Naturally, if you follow another plan, the plan 1 using Proteus, or the plan 2 using Wolfram Alpha, or the plan 4, for example, by means of electronic design automation tools using BHDL, you have another mechanics, you have another procedure to follow. But this is what you have to attach to every one of the solutions that you like to solve here. So once you have selected the method, the next step is to plan something like this, a sequence of operation, if possible with intermediate results that you can check with your colleagues, so that you can go advancing to the next step and to the final solution. And probably if you've got the truth table, right, you can continue testing the results of the truth table. Let's see if the truth table is the right one or not. Comparing with your colleagues, that's one way. Let's see if you've got the same number of maxterms with the same indexes. You can do that with your colleagues, and there is a better way. You can compare the truth table with the one that you got from other methods. That's the point. Even if you are planning the solving of a circuit by means of 4 different methods, doesn't matter. In the end, you have to reach the same truth table all the time. That's the key point of doing that thing, of inventing several methods, so that you can feel comfortable even if you are alone. Because if you work a little bit more using another method, You can work in parallel, and in the end you have the same solution. That is a good way to go on, right? So if you have a circuit like this, you know, it is perhaps too large, so why don't you go, as you know, section by section, imagining that you have here several circuits, and this consists of naming, for example, this wire, for example, this can be named T, perhaps this one can be named V, you know that. Then this one can be named F, for example, if you like, or that one can be named F, and this is, for example, Z, and this is, for example, R. All right, just give a name to the wire, so now you can solve the problem, which is, you know, let's find the equation, the circuit's equation, you know. It's going to be something like this. Key is going to be R or V, and so R or F or T, right? Something like this. There are several ors here, right? And now, if you like, R becomes Z and A. Okay. F becomes, you know, something like D0 short A. Okay. And then not, because you've got this not here, right? And this and with B. And the T, for example, is the larger one, so you can separate that very well. So T is going to be, you see, D1 or D0 or B, and now you have a NOR, so it's a not, and then you have another not, like that. So this is this term, and then there is a product here, right? There is an AND with another term, which is D1 not or A or B. And the same as before, you have a not, and finally another not. That way, so this is the other term. But finally you have that this goes connected with a OR to another term, which is B or B. Okay, this is the term. So here you are D0, A short A naught, and B. So this is the expression of the T. So here you are. So in the end, you know, the equation that you have to go simplifying is simply, well, Z, it is, you can calculate Z D0 naught B and B or d1 naught or d0, like that. So this is z. Okay, so z goes here, everything is ended with a, this is r, and then f becomes this term here, d0, short a, not and b, and the t becomes something like this, right? So that's the expression of the equation t. Very well. Okay, so this big expression is like that, and this big expression, you see, the point is that you can go back to the secant. So you are doing nothing now but translating the secant k, which is now a picture, a logic diagram, into an equation. So that's the first step, the initial step. And you know that now that from an equation like this, if you like, you can write it, you can translate the equation, for example, into BHDL, and that is going to be the method 4. Or instead, you can translate or rewrite the same equation using Wolfram alpha style. So this is going to be the method 2. So you can try to type in this equation into Wolfram alpha, you know, and so this is the method 2. But now, because we are trying to develop the method 3, we will try to simplify. All right, we will try to simplify this equation just like that, thinking about and applying the Boole's algebra postulates and theorems and the like. Okay, so this is the equation that we will simplify in some way or another using Boole's algebra. So this was the t, and you know the other terms, the z, the r, and the d. So in the end you have this expression. Be careful, because here from the previous equation we have a different value, and then there is this big not here that takes it all as the final NAND that you have to generate the t value. And here you also have the a, right? The AND a, that was the final value from this term. So this is the equation, and now it is better for you to go step by step, term by term again. So for example, the term b, let's just start with this one, which is, you know, it looks simpler. So this is b d0 sure a not. So this is, you know, not or exclusive. So in this way, this is the kind of the identity function, the opposite of the sure. So very good. This is b. In some way, the sure is d0 a not and or d0 not a. So, and because it's not, this is, you know, b d0 a not or d0a, like that. Okay, so you can demonstrate that. Okay, you can demonstrate that, so that in the end this is b d0 not a not or b d0 a. So here you are assume, you see this is a sum of two products. Very well. So this is what we want, to transform something like this into something very simple, like a sum of two products. So that we can add now two more products, like those ones here. You see? Here you have clearly two more products. So this is very well D0, not B, and A, or D1 not D0 A. So here you are another sum of two products. So finally, what is left here to analyze in some way looks complicated, but I think that is not that so, is this big bracket here with the two terms and then the not. This is not complicated because in the end here you can identify very well that this is the same thing two times, and this thing here is nothing but x not. So this is simply x. So in the end this term is a lot simpler, okay, and is looking like it is just d1 or d0 or b, that's it, without the not, and here you are the same stuff. So you can see b or d1 not or d0 not or a, but now like that, you see, because you get rid of the two parentheses, so it is like this, and the final, now yes, the final not, that takes it all. So now it is clear that you have again x and y not, which is transformed into x not or y not, something like this. Okay, so let's go on with this expression. So this expression is going to be, you can very well continue here, d1, d0, b not, because this is what we call x, or b, d1 not, d0 not, a not. That's it. So now you see, because we like to have products, and instead of sums, you know, we can apply here another rule, another mechanism, which is x or y or z not is simply x not and y not and z not, something like this, you see. So in the end this expression becomes something like d1, okay, now you can go term by term, d1 not and d0 not and b not, or, because you keep the or, b not and d1 not, so d1, d0 not, so d0 and a not finally. So you have finally two more simple terms, which happens to be products. So in the end you can write here, if you like, the key, which is this function again, a function of d1, d0, a and b. So this key may be considered a sum of products, right? Sum of products is just d1 not and d0 not and b not, or b not, d1, d0 a, or a not, or the one that we've got here, which is the one there, for example, b, d0 not, a not, or b, d0 a, and finally the one here which is in red, d0 not, b, a, or d1 not, b, d0, a. That's it. So this is the key, okay? Now as a sum of products, you see? That's the function. So you have a sum of 1, 2, 3, 4, 5, 6 terms. And if you realize that only one of the terms contains all the variables, reorder it in another way, but you know, this has all the variables. So this is a single max term, single minterm, right? But not the others. The others, in order to get minterms has to be modified in some way or another to add the missing variables in each one. So from a term like this, you can introduce the dig1, so in the end you have two minterms instead of this simple product. And if you have two minterms, you have two terms in the two table, which happens to be one. So be aware, because I realize now that there is still an error here. This is D0 not B not, okay? And this term is the same as here, D0 not B not, and now and A, just with the other one. So finally, those are the expressions that you have to go, converting now. You see, this is the initial equation, this is the sum of products, and so now the mission is to get the sum of minterms, all right? And in order to get the sum of minterms, we can very well go product by product, okay? So take another sheet of paper and continue the analysis, because it's very simple now, because what you have to do is apply all the time the same mechanism, okay? For example, this one here, this term that goes fast, this term happens to be D1 not, D0 not, so the missing variable is the A, so you can say B not and now A, or A not, because this is all the time a 1, right? This is all the time a 1, so it's no meaning here. So the idea of adding variables, adding the missing variables, is that simple here as imagining that you have x the same as x, y, or y not, because this is a 1 all the time, right? So this is two products. Instead of a single literal, now you have two products, which is x, y, or x, y not. This is exactly the same thing. So this is what you are going to apply here to transform a single product into two minterms, because now you have D1 not, D0 not, B not, A, okay, but now why not? Well, let's do that in another step, which is going to be easier. So D1 not, D0 not, B not, A not. So now you have the four variables, but be careful because they are not ordered, you see? Disordered yet. So be careful, because now you have to have another step here, which is organize the variables in this way. D1, D0, A and B. So now you have a product, not a max term. The max term is now when you order the variable. So this is going to be D1 not, D0 not, A and B not. This one and the other one, which is D1 not, D0 not, A not, and B not. Alright? So this is the minterm or another minterm. And which one? Because we talk about minterms, right? A minterm, when you have a term which is not, is a 0, taken as a 0. So you have a 0, and a 1, because A it's just like that, literal A. So because of this and because we talk about minterms, this is a 1 and then another 0 here. And here you have 0, 0, 0, 0, right? That way. So this is the minterm 2 or the minterm 0. So now, from this term, you know two terms of the truth table. So now you can go and compose the truth table, because the initial expression do not exist anymore. But what you've got now is a sum of products. Remember, you see, to check that with other colleagues or with other methods, because now, you may make mistakes all the time here. So now is when you have to handle the truth table from D1, D0, A and B, and key. So 0, 0, 0, 0, you see, this term is already a 1. So this is what you've got from this analysis. And you know nothing about any other term, but the 2. The 2 happens to be a minterm as well, okay? So now you can go composing this table like this. It's not like that, I go too fast. So it's 0, 1, 0, 0, 0, 1, 0, 1. 1, 1, 1, 0, and finally 1, 1, 1, 1. This is the table. All the possibilities, 16 possibilities. So I've got 2 of them. The next term is easier, okay? Because you already have the 4 variables here. The only thing that you have to do now is reorder it correctly. So this is going to be the minterm D1 and D0 and A0 and B0, which happens to be the minterm, okay, 1, 1, 0, 0, I guess. So this is the minterm 12, because 1, 1, 0, 0 is the combination 12. And you know that because you can all the time remember that this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 in decimal. So this is the value you've got here. So this is a minterm. So this is a 1. Okay. And so on and so forth until you get them all, because you see most of the terms has only 3 variables, so there is only 1 variable missing here. So any one of these terms is going to generate 2 minterms, and perhaps some of them are going to be repeated, but that's not a problem. If you find another, from any one of these terms, you find another minterm 2 or minterm 2 or minterm 2, so you don't have to worry because this is x or x or x and this is simply x. So doesn't matter if you have the minterm repeated 2 or 3 times because you have several terms, because the 3 of them simply represents the minterm, right? So 1 time, so that's the way. Okay, so now I can guess that you can go to the end here the same way I've analyzed this, so you can go and continue the analysis of the other 4 terms. So in the end, what you are going to got here is something like this. The 0 is going to be 1, the 1 is going to be 1, the 2, have you seen, is 1, then the 6 is going to be 1 as well, the 7, another 1, finally the 9 is going to be another 1 of this function, the 10 is going to be another 1, the 12 and the 15. So those are the ones. So the other ones, the 3, the 4, the 5, the 8, the 11 and the 13 and the 14 are going to be 0. So finally the solution of this problem is going to look like this. Key is a function of d1, d0, a and b, and this is nothing but a sum of the minterms. Now you can add them all into this series, the minterm 0 as simply as a decimal indexes, 0, 1, 2, 6, 7, 9 and 10, okay, 12 and 15. That's it. That's the solution of the 2 table. Or if you like, you can take not the ones but the zeros. The ones which are not ones are going to be zeros. So now is your turn to rewrite again key as a function of d1, d0, a and b, like this. You see, a product of the max terms that are going to be considered accordingly to the indexes in decimal. The 3 goes first, okay, the 4, the 5, right, and then the 8 and the 11, and finally you have to account for the 13 and the 14. So in the end, this is the solution of the problem that you can compare very well with the other methods. Okay, remember, for example, let me explain it you again. You can take the picture of the logic diagram and capture it in Proteus and run the simulation. So click, 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 click 16 times, you get the table. Almost in a lot more easy way than this, but you get that what you want, which is the truth table. And then this is another way. Go term by term through this intermediate sum of products until you find what you want, which is this, you see, sum of minterms. All right, that's another way to go through the table. And finally, or in another method, you can go and from the initial equation you can copy it in Wolfram alpha and get the same result. A kind of a table. Remember that perhaps the columns are disordered, but from this table you can very well capture which one of the minterms and maxterms, and so you can get the same result. Or finally, the same equation can be written very well in VHDL, because this is what we are going to do all the time this semester. We will translate everything into VHDL, so why not start like this in this example? Take the second key and copy it as an equation in VHDL, which is going to be the architecture of a final file, you know, that can be synthesized into a circuit, and finally you can simulate and get the logic diagram, which will become the resource from which to get the truth table. Again, the same way, combination by combination, right? So that's another example. So that's what you have to do now. Just go through several exercises like this and try to be comfortable with products, sums, maxterms, minterms, truth tables, and the basic operations using Boole's algebra.